Welcome to Chapter 6. In this chapter, we are going to talk about magnetic materials, the special class of materials that respond to magnetic fields in fascinating ways. From the hard magnets in your computer's hard drive that help store digital data to the soft magnets that operate quietly inside transformers, motors, MRI machines, magnetic materials are everywhere. What makes them tick? Why do some materials get magnetized while others don't? And how do engineers harness this invisible force to power innovation? In this chapter, we will uncover the physics behind magnetic behavior, learn about different types of magnetism, and explore the industrial and technological roles of magnetic materials. Whether it's powering medical imaging or enabling this energy grid, magnetism is a silent driver of modern life, and we're about to discover how it all works. Let's get started. What you see here is a simple but powerful concept. When an electric current flows through a loop, like the one shown on the right, it generates a magnetic field. This field isn't just an abstract idea, it's made visible through what we call magnetic flux lines. These lines shows us the direction and strength of the magnetic field, like invisible threads wrapping around the current loop. The vector H, which represents the magnetic field intensity, tells us both the direction and the magnitude of the magnetic force at any given point. So, in essence, moving electric charges, like the spinning electron in its loop, create magnetism, and this invisible field becomes a key force we can harness in real world applications. Some materials are naturally magnetic. They don't need any electrical current to produce a magnetic field. A classic example is the bar magnet, like the one shown on the right. This simple object holds a magnetic dipole with a north and south pole. The magnetic field lines loop from one end to the other, creating a clear direction of magnetic force. Why does this matter? Because it gives one of magnetism's most powerful and useful properties, attraction. This is the force behind everything from fridge magnets to magnetic locks, and it all starts with this basic dipole behavior. The image on the right shows two bar magnets placed close together, and here's something important to notice. Their opposite poles are aligned. This pairing of magnetic dipoles isn't just about attraction at the surface, it reflects a deeper atomic level interaction, the way electron orbitals align in magnetic materials. So, even though these magnets are macroscopic objects, they represent what's happening at a much smaller scale. The dipole interaction is what gives magnetic materials their strength and structure. In free space, that is where there is no material, a magnetic field sources creates something called induction, where we refer to as B, and its size is known as the flux density. This induction is linked to magnetic field strength, or H, and they are related through a Keyes equation. B equals to mu 0 H, where mu 0 is the permeability of vacuum. Now, if we place a solid material inside that magnetic field, say a piece of iron, things change. The new relationship becomes P equal to nu H, where nu is the permeability of the solid material. The image shows two cases side by side, one in air and the other with a magnetic core inside the coil, and how this core boosts the field strength due to its material's high permeability. Now, this part makes a cool connection between magnetism and something we already know well, Ohm's law from electricity. Ohm's law tells us that V is equal to I times R, voltage equals current times resistance. And with some substitutions from resistivity and conductivity, we get another form which compares current density with the voltage gradient. In magnetism, we draw a smaller parallel. Magnetic induction, B, is like current density. Magnetic field strength, H, is the voltage gradient. And permeability, mu, is like conductivity. When we place a solid material into the magnetic field, it contributes its own magnetic effect. We call this magnetization and represented by M. So total magnetic induction becomes, as you see on the slide. That last part, H plus M, tells us the material not only feels the external magnetic field, but adds its own internal response. The diagram on the right shows a magnetic core being magnetized, and to find the field inside. Let's wrap up with the units used in magnetism. On the left, you'll see the equation for relative permeability. Nu r is equal to nu divided by nu zero. This compares how easily a material becomes magnetized how easily a vacuum does. Nu zero is a constant, the permeability of free space. Now, take a look at the table. It gives us the SI units and their CGS YIMU, what means centimeter gram seconds equivalents for each key magnetic quantity. Magnetic induction is measured in Tesla, but in CGS system, it's called a Gauss. 1 Tesla equals to 10,000 Gauss. Magnetic field strength is in amp turns per meter, but it's called an Oersted in CGS system. Magnetization uses the same amp turns per meter in SI, but Maxwell divided by centimeter in CGS. Permeability is measured in Henry per meter, and in CGS it's technically unitless, since nu zero is set to 1 in that system. And finally, relative permeability is just unitless ratio in both systems. This table helps bridge the gap between different unit systems you might see in textbooks or research papers. Some materials, like copper and gold, have a relative permeability slightly less than 1. These materials are diamagnetic. That means that electrons slightly oppose an applied magnetic field by generating their own weak opposing field. On the other hand, many solids have a relative permeability just over 1, usually between 1 and 1.01. These are paramagnetic materials. They reinforce the applied field even if only slightly. On the right side, the diagram helps us visualize this difference. Diamagnetic materials have paired electrons and they are repelled by a magnetic field. Paramagnetic materials have unpaired electrons, making them attracted to the fields. While the magnetic effects in both types are quite weak, they come from the material's electronic structure. That is, how electrons are arranged in atomic orbitals. So even though all materials technically show diamagnetism, in atoms with unpaired electrons, paramagnetism tends to dominate. In some materials, as the magnetic field increases, the magnetic induction doesn't just rise steadily, it dramatically increases. These are ferromagnetic materials, and they have been historically associated with iron and iron containing compounds. Unlike diamagnetic or paramagnetic materials, which have relative permeabilities close to 1, ferromagnetic materials can have values well above 1, even reaching into the millions. What makes this possible? It's the interaction between electrons and neighboring ions. These materials have unpaired electrons that strongly align under an external field, resulting in intense magnetization. And here's the key part. They can retain that magnetization even after the field is removed. That's what we call permanent magnets. On the right, the hysteresis loop shows that magnetic memory, the way ferromagnetic materials stay magnetized even when the field goes to zero. So, ferromagnetism isn't just strong, it's also persistent. Unlike ferromagnetism, where all the atomic magnets align in the same direction, ferromagnetic materials have opposing magnetic moments. But here's the twist, they don't completely cancel each other out. These materials, like many ceramic magnets, contain atoms with different magnetic strengths. So, even though some magnetic moments point in opposite directions, the stronger ones win out, resulting in a net magnetization. On the right, you can see how this compares to other types. Ferromagnetic spins align. Antiferromagnetic ones cancel out completely, but ferromagnetic moments are unevenly opposed, leading to partial cancellation. And that's why they still act like magnets. This mechanism is especially useful in things like transformer cores and magnetic storage, where you need stable, reliable magnetism without relying on metal-based magnets. Let's wrap up our look about magnetic materials with the building blocks of modern magnetism. From iron, which powers electric motors and transformers, to the neodymium magnets that spin inside your computer's hard drive. These elements are the backbone of today's magnetic tech. And there's more. Nickel stands out with its flexibility and corrosion resistance, while cobalt performs reliably even at high temperatures, making it ideal for aerospace and energy applications. Each of these materials has its own role. Some offer strength, some offer stability, and together they enable an incredible range of from devices from medical imaging systems to cutting-edge electronics. As we continue to push the boundaries of technology, these magnetic materials remain fundamental, often hidden, but always essential. Iron is the most widely used magnetic material. It's strong, abundant, and easy to shape, making it perfect for motors, transformers, and cores in electrical machines. It's the backbone of everyday magnetic applications. Neodymium is part of the rare earth family and creates the most powerful permanent magnets we know. These magnets are compact but incredibly strong, which is why they are used in hard drives, earbuds, wind turbines, and electrical vehicles. Has a moderate magnetic strength but stands out for its resistance to corrosion and wear. It's often used in combination with other metals and in coating applications where both durability and magnetism are needed. Cobalt remains magnetic even at high temperatures, which makes it essential in aerospace and high performance motors. It's also used in magnetic alloys that need to stay stable under heat and stress. So, as we wrap up our journey through magnetic materials, we have seen how elements like iron, neodymium, nickel, and cobalt play critical roles in shaping the technology around us. From tiny hard drives to massive power systems, we have uncovered the science between magnetic fields, permeability, and the different magnetic behaviors like paramagnetism, diamagnetism, and ferromagnetism. Whether it's the powerful pull of a neodymium magnet or the steady performance of cobalt under high heat, each material brings unique value to the world of electromagnetics. In the next chapter, we will dive into the world of resistors, those tiny components that manage electrical current in every circuit you have ever used. We will explore how resistors control voltage and current, how they are designed, and why their resistance matters so much in everything from LED lighting to precision medical instruments. Get ready to uncover how something so small plays such a big role in the reliability and safety of electronic systems. See you on next chapter.